All right. Let's begin. We stop at this. There is some one. Time T. So this is what the representative of the total population. The minimum. So and Z. No, here. Speak parameters. Okay. I'm not talking about the branching process. The same, it's some other project. Then it's starting with one and ID implements on the same distribution as of the branching process. So XI has the same distribution as of the branching process. And we are getting ID. We define some special type. This we said three times. The same distribution as time T total. Any doubts on this? What this capital T is, what capital T line is? Why this is actually is. So we're not counting generation after generation. So this will not give me what is the number of projects in a particular generation. But looking at a total number, it counts right. It's not going generation. But each prime was very related to the process where we are randomly. So let's call this a random walk person. Unexplored. So no, that I included in addition to make sure that that had the same law. So that was just to show that T prime had the same distribution. So this is your random walk process. All there is that this has the same distribution. Every time I'm adding an independent random variable, so the same distribution as the number of children in my branching process. So that's all the process is. And that's my T prime. What I told last time was that T prime has the same distribution as T, which is the total number of projects you're going to see in your branching process. To show this, we included an extra process. Explore. So the typo in the book is that there is this I prime, so it's a 0. It's 0. That's not correct. That's usually one. That's where the process. That's a typo. So we can you model the difference explode versus and so and this this has nothing to do with it. It's a very simple process. That's why I'm calling it a random walk. Every time at time I, wherever I am, I'm adding a new random variable xi and subtracting, so taking one step back. So if you want to think of this as a integral. You're starting at this point. What am I doing? I'm making xi gems first. And then taking one step back every time. Wherever I am. That's all. So nothing to do with my exploration or exploration. Okay. Point is that this process is nothing but the way the branching process is actually evolving in terms of total number of items. Not in terms of generation after that. Because here there is no sense of direction, or there is no sense of topology. I don't care how you actually do it. So that is why we connected it to explore versus RX. It's possible. Okay, so now I ask you to do something one small exercise. So remember, K that's what you should do. And eta let's say, is my extinction property. Now, look at PTA parameter, which is theta to the power of 2 minutes. So if theta is 1, there is no change. So the non-trivial factor you should only worry about theta less than 1. Now the first thing to check is if I want to do something interesting, the PK is a middle value distribution. That was the exercise. Anybody finish it? Oh,
you just take the sum over k.
okay, so summation PK prime over k. We want this to be equal to 1.
1. So on the right side, it's equal to 1 over eta and k pk.
1 over eta and eta over k.
pk.
That's why that is.
Yeah. So it is just a generating function. So this is equal to g
1 over eta g of x.
Yeah.
X.
X eta.
X is fine.
So g of x eta is eta.
So many ways this is one shot. This is in fact probability distribution. Now can you connect? So what are your photos? This is something interesting. So think about eta to be less than 1. If eta is greater than 1, what we are going to say? Eta equal to 1, what we are going to say? Now eta is less than 1. What does it mean? That there is non-trivial probability of extinction, non-trivial probability of survival. Now condition on extinction. What do you think is the distribution? So, okay. So these are the exercises I'm adding every time. So if I condition on extinction, what is the distribution of this new exercise? Can you say something else? Or equivalently in terms of our branching process. So it starts one particular which is going on. So let's keep this is generation 1 and generation 2. I'm conditioning on extinction. What do you think is now the new distribution of each of these number of progeny being generated? It will remain the same. That much you can convince yourself. Yes. Because each particular no. So what you should first is identically distributed as what they do. What is identically distributed? The number of children born at time 1, number of children born at any node at generation 2 and so on. So you should first convince yourself that this is at least identically distributed, even if I condition on extinction. Now the fact is, given that I'm conditioning on extinction, what is the probability that now x takes the value k conditioned on extinction? So what does it change? Has anything changed to you? The question here, what we are after? So here, see, with eta less than 1, there is a non-trivial probability of sometimes you will get extinct, sometimes you won't get it. Now, putting all my attention to only the cases where I do go extinct. In that subset, what is the distribution of the number of children born to any particular node? First of all, does it change? And if it does change, what do you expect to happen? Should have some connection to it. That much is clear. When keep writing x for the generic random variable, which denotes the number of things in one. Targeting the level at which I'm making the words. So at least qualitatively we should say should decrease, increase, decrease. Okay, then you can convincing argument that it should. Or rather it cannot increase. Either of them is fine. For k equal to 0, it should increase. For k equal to 0. Yeah, so what does that mean?
Just normal probability x equal to 0. You compare that with the conditional probability x equal to 0. Condition that it goes extreme.
Okay. Anything more?
A greater than 0, it should decrease.
So expectation in this subspace, expectation of x is less than 1. How do you do that? Because that's a very strong statement. No, yeah, based on extinction, right? If I only focus on the subspace where things are getting extinct, then in that subspace, expectation of x should be less than 1. And if I look at the whole subspace, then some of the weight should shift towards other x's. So you can't take what you say is correct. But directly going from here to that jump is slightly different. So first what you have to do is to do this and then claim that eta equal to 1 is the only solution for the new distribution. So once you can characterize this distribution, then for that new distribution, you have to find or to show rather that for the new distribution, eta equal to 1 is the only solution. One way to do that is to show that expected value of that new random variable is less than 1. That because we already show that if any branching process is expected value less than 1, then it definitely fixed. So your intuition is spot on. This little bit of right direction. So what you're saying is right. I'm just saying how to mathematically say it is what is the extra step. If you show this distribution, show that the expected value is less than 1. Because the process on its own need not have extremes. It's just that you're conditioning on that. So that's why you have to study it. So I claim that pk prime is the new distribution. Yes. Anybody see why? You can give me a special case also. The claim that it is nothing but the quantity is eta power k minus 1 times. Where pk was the original probability of x equal. That's the case. That is why we needed to make sure that pk prime is valid distribution. Any hand-wavy argument is okay. Any special case is okay. Very peculiar. It's going to the power k minus 1. But there is a good reason for it. Why k power? The power is k minus 1. What does extinction mean in terms of this process? That's all I'm conditioning. That the process would extinct. What does it mean? Then it has to get extinct on every possible progeny, right? However you branch out, all of them have to get X. Does it help? This observation to see this. It can't be that on one branch it is not going extinct. So there is not extinct. So every possible branch is going extinct.
Yes, so that conditional probability can be written as probability x equals to k and
Okay.
extinction
Okay.
divided by probability
That-
x. And the means numerator thing will be eta to the power k.
That is very good. Right here. So you're saying that you have to write this. Given that we call it E, this one. Then basically. Divided by. Okay, now, what are you saying here?
That thing.
Denominator I. The numerator is what you do. Yeah. You say something, right?
Probability of means x equals to k was pk as we know,
That much we know, yes.
and every progeny in that level should be extincting
Yes.
for that probability. So
Fine.
eta will get multiplied with itself k times.
But tell me how to write this. You're spot on. What you're saying is that given that x was k, extinction happens only if all possible branches extinction. And what is that probability? Because from that level downwards, everything is independent. So eta to the power k has to happen. So which direction should I go? I just need to write it for them. So why don't you move it down? What is the probability? That when he has given x is equal to k times probability of x equal to this. Now, what should happen? These guys are e to the power k, which is pk, and then divide this by eta. So this is slightly sloppy, but I'm not very wise. So understanding this because you should really do that as generation one. I should really have it. Then Z1 is equal to k and then because yeah, there's good reason to do that. So long as you understand what is going on. Everybody follow what is doing? Here to here over diagram. Because even so, you should really think of first generation. So suppose Z1 was k, which is nothing but the same distribution as x. So we should really think of x as Z1. Now Z1 is k. K. Now, for my extinction to happen, all these branches have to go. This has to go extinct, this has to go extinct, and this. And everything below is independent of what is happening. So this better be that exponential probability. This probability. That is precisely what I'm saying. So for one such example, you can actually show that this is nothing but that. The code actually does something stronger. And there is a gap that I not understood, but I just write a gap and figure this other parts of the code. If you can figure out, we will fill it up the next time. So it will be a good guess. But not being able to wrap my head around. So what really is trying to do is extension for. So what rather way of writing extension, given that we have definition for T prime? T prime is long. T prime is the time at which the xi process goes to T. The SI process goes to T. And that is nothing but the time at which the process stops. So simply this implies that T prime is less than. That's what it is. What we are really after is what is the probability of T? T1, T1. That's really what it is after. It lies in a very complicated fashion. And that's where I'll tell you this precise point. I don't know why that is. And in particular, let's say this is. I just want to know the full distribution of T prime, given that T prime is standard. That is all I want to know. Should be T prime.
Right.
Little T for all Ti.
No, this one, condition.
That's it. This is what my degree distribution I should be trying to find. What is T prime by definition? So T prime equal to T. What are the places? What does it mean in terms of our process? It means that x1 plus x2 xt should be equal to T minus 1. And correct. Yes. That's a good definition of my SI prime process. What was the definition of T prime? T prime was the first time. T prime equal to T means that is the first time at which the SI process goes to zero. This is true. For some reason, the book says this is true. I don't put it in this. You see it there. I don't see it filed. So this fact, everything else is fine.
In the title, maybe not a I will want to T minus 1 could be considered independent, but the last one has to.
But see, there is dependence on all of them.
Yes.
What you're saying is right, that up to T minus 1, I can make them independent and push all the dependencies in the last one. At least that much should be there.
Yes.
But no, this is not a type. There's some reason that this is in fact is correct. I can't wrap my head. I spent enough time, I've looked at alternate tools, they're so ugly that I came back to this. So with modulo this will do everything. This suppose seems to be true. Why? So now what I want to find is this point. Do exactly the same logic as before. So for any T less than infinity about the characteristics. What should I do? I should write this as P equal to intersection. What is this numerator? Remember, little d is finite. So this is nothing but probability one. Little right? Little d is.
P prime could be arbitrarily large, but it doesn't. I don't understand this P prime.
This itself you know.
Yeah. So P prime
Extinction means what? The extinction means that t prime is finite.
it's fine.
That's all I'm saying. Given that you're going to get extinct, what is the t you're going to see? See, it's not a deterministic quantity. Is that clear? So let's look at the random person. So suppose this one top here, this one top here, this one and but all of them are going extinct. Now, what is the last level essentially? You can think of it. But we're not looking at this direction. All we're looking at is if I keep walking around, how many steps I will have finished all the exploration. Think about that. That's the time. Okay. So that given that so what I'm told that t is finite. Now given that t is finite, there's still a lot of that. Even if I tell you what that value is, okay, I don't get to see. So think about Gaussian random variable. So any random variable in space. This infinity, I can't give you a simple example where infinity is included in the sample space. This is one process where the number of particles can be in the process goes on forever. So all our information I'm telling you is there's not infinite. So it is finite. Now given that it is finite, what is its distribution? That's all we're trying.
But P prime can be arbitrarily large.
P prime can be. That's the whole point. Otherwise, if eta was 1, then it is with probability 1, t prime is less than infinity.
Yes.
It's only in the interesting cases when eta is not equal to 1, then you do something else. This is event clear that given the fact that the process dies out eventually, what are you likely to see as its population? That's what this number is. This is the population size. This is the fact that the population is finite. Well, what is not equal to 2. So this is now okay. So this is nothing but 1 by eta. P on. Now how should I go first? I can open this up using this. Okay. Is that what I said I would do? So I have this PK times, right? How do you use that? Remember the relationship. P prime k is eta to the power k minus 1 times p. So now I want to get them involved here. So what I want to show is this after all of this, I think that's all I want to show. This is what I want to show. Down to couple of steps. The formula I know, so I just easily plant it. So P prime what is P prime times
to the power x I minus
minus, right? Everything is flipped.
Minus x plus 1.
Yes. Okay. Now can you observe something? Why should I go from here to here? If you look at this condition, use this. The x1 plus x2, given the fact that t prime is written t, we have this condition that all of them sum to t minus 1. And all of these are sitting here in power, all of them have. So what will remain here? Something will remain. T versus the slide. You should get. To the power how much? So T definitely. And remember I'm starting minus. Side. This is equal to T. We cancel out. And reference theta to the minus 1. Only one more side. I want to get a beta was.
That sum is
T minus.
T minus.
Hmm.
This is beta. This is a mess. But it's just will not be there. But as long as we believe that we're able to show that the distribution of the number of particles given that is finite is nothing but a new distribution coming from the primes, and that's why it's called a dual. This is called a dual probability distribution of atoms. And now we can claim motivation. The fact is now this is subcritical always. Why? So conditioned on the process to go to extinct, what you show is the new distribution is the dual distribution. Now, if I can show that the expected value of the dual distribution is less than 1 and that. Right, because the meta theorem. Am I jumping ahead? Something seems to be off.
So could you explain that again? Sorry,
No, it's okay. From here to here. So what does it mean? For any t finite, t prime is equal to t given that t prime is less than infinity. Okay. Which is covered.
yes.
And then I'm just writing it in units. That's the only problem I really have. The matter thing, but there's two sides. We don't know what it is. Subsidy argument short. Not obvious. The way I thought about it was essentially there are t independent random variables which are going to define this event. So in terms of law, I can understand by probability law that the collection of these independent random variables is going to define that event. What is the product? That part is. We'll see that sometime. Hopefully, we will. Rest is okay. Now, what do I want to do? I want to say this new process. One is sufficient to show the expected value with respect to x prime. This is obvious by x. Simplify the triangle.
Because of process dice on that.
No, just direct computation. Eta is this guy's extension probability. That's all you really have to use to claim that this is the variable. Something very similar to what you prove for showing that this is probability distribution. Very similar. When I do leave something as a file, this is just to replace you becoming one of the first. Do solve it. If you don't get it, we'll solve it. Most likely you won't find it in the homework. So that might be the only way to actually go through the class again. It's not a real exercise. Okay, so now you said something about given that we go extinct. What is the distribution? What now I want to say is about. Suppose go back to X. That's a supercritical process. Will solve it. How to estimate this problem? One way is to do whatever it is. In terms of the events we have defined for ourselves, what does this correspond to? You can look at the S process. We can be greater than equal to K. What is it defined in terms of S? S remember what X from plus minus I minus. Prime equal to K. What is it defined in terms of S?
Star is after S.
No, S K is 0. That's what it is. Right. So in terms of X10, what will it mean? That X1, yeah, X2, X3 is fine. Then K. This implies that this sum is less than equal to. So if you want to estimate this probability, how can I write it as a sum in testing summation? With identical. Usually you want to apply channel, let me give you. Concept. At most probability want some of the ability is yes. Yes. That's the same thing as that's probability is of your okay. If I could imply that is summation better be less than k. So I want to count everything above k. So I can fix s is equal to k, s equal to k plus 1 and keep going upwards. For that one particular s, this is the problem. Now, this we did something using Chernobyl, you remember? Chernobyl goes both ways. The summation exercise being greater than something, summation exercise less than something, as long as something happens. What is that something? A. That much you should have expected that. Now I want the reverse. What I was saying here that the sum is less than something. So for this probability to be small, the expectation value of each of them should be large. But at least one will work on that is why we have this thing. Where the expected value of the probability is at least one. Can you repeat it again? Yeah. What is the probability I'm after? Trying to control the probability that the sum is smaller than the number. This is going to be small. Only if each of these random variables have a large enough mean. If this mean was 0, I should not be able to control this probability. Because then easily this can happen. That is why this is the correct condition. And this is exactly where they're not counted. This can be the problem. This is the right there. E to the power of I. Derived from the rate function. And right to the power. Scaling agent. We did all this in we should start over and do it. It's also over and over. A equal to 1, that's why I'm substituting this writing that.
You can use e to the power t.
This one, x. X means this is called the rate function. With the Chernobyl, we are getting positive exponential. And whatever the exponent is called, the rate function. 0 is. Okay, so what does the sum look like? Exponential sum. Sum from is equal to rate. Here is the constant. That's one thing. What is p to the minus p? Integral of e to the minus p.
Geometrics.
Yeah, it's like e to the minus x over 1 minus e to the minus 6. That's what it is. Think of integral. That's much easier. What is integral of e to the minus x? Minus e to the minus 6. Lower limit is k, upper limit is infinity. So that upper limit is 4. Some y is slightly different. So what you end up getting is that is going to be at most. You can actually control this property. This doesn't matter. These are the intermediate triggers. Eventually, we'll do another interesting theorem just like the previous one. What it was, if it is critical, the process looks like sorry, conditioned on extinction, the process looks like a subcritical branching process. It is the opposite also. Conditioned on not extinction. What is the process? Any guesses? You get to that.
What, why are we calling it subcritical?
Subcritical is because any process whose eta is 1 is called subcritical. Any process whose eta is not trivial is supercritical. Criticality is exactly at 1, so that also is supercritical. So that's just a name. But punchline is that the newer process is subcritical. That's a condition on the process to die out. The distribution has. You can say that was by definition. That's what your argument really was. That once I have condition of it dying out, I cannot find clusters with area or run population cannot do this. This is also I'm putting that in mathematics. So now, just to rejig your marking, everybody remembers. And was marking here. There are many ways to test like what I write typically to the have to contain this. That's a definition of market. Okay, so now I want to know this. Want to prove the following. Some random variable which is called let's try to pass. Z is the usual number of particles at level n. That's what it is. We did a simple exercise. What is the expected value of Z?
Power n.
Oh, good to the power. Now, if I want to show something like this, and I'm giving you the hint that martingale is somehow useful. We did some theorem about martingales, which was on this layer. That if something is martingale, something happens, I'm sure. So it was called martingale calculus there. What did it say? Do you remember the statement? It's a basic definition.
Expected value of Mn will be equals to that means M0 something like that.
It's a convergence theorem. Convergence theorems are the type that the sequence converges to something in distribution and probability or what really you want. So okay, that I'll let you see. But first tell me what is the martingale here? Can you observe something is a martingale? Then I can apply martingale that. What do you see as a martingale? Very little word. I have these evidence. Is that a martingale? Check.
Taking value of Zn plus 1 given that Zn
Correct.
is equal to Z.
P of H. It's view time.
So it's mutual.
So what's the next try?
Zn by mu.
Okay, Zn by mu. Does that work? So Zn itself is not.
What is the condition for it to be available?
Total estimated value of Zn plus 1. Given Zn. Everything else, anyway, it doesn't depend on. I can simply say that. Few times there. This doesn't work. What can you make it work? How can you do that? There is 5 published. Then if I divide u to the power n plus 1 on both sides, what will I get? I get Zn plus the power of n plus 1. Magically, this process is the correct thing. So, go to the really first notice the property that Zn power n. You also have to see that it's not blowing out. This process blowing out. To understand the meaning, I will write down. But is Zn by mu to the power? Mu is a number greater than 1. Very important thing. So if mu is less than 1, it will go over to infinity. So, what kind of process is Zn by mu? Does it remain bounded? In some sense. What is the expected value of this? Zn by mu. 1. That's good or bad? Like, for convergence theorem, what do you want? You want something less than 1. That will blow up. So, another fact is what say is that this. Both these conditions are required for an artificial convergence theorem. Then this directly is implied that it does go to a random variable, which is also bounded. That's the important. So this is LB here. It's a martingale. This is an important one. It's very difficult to actually characterize more than that. But what exactly is the distribution? That's an important point. It's headed by V1 for a supercritical process. It's not innocuous thing. What does it mean? This is a supercritical process. What does it mean? That Zn divided by V1 is converted into a bounded triangle. Is it expected?
means with probability 1 Zn is of the order mu n.
Usually, yes. It's very slippery to always invert the random variables. Very slippery. Because argument, you could say all random variables added together are something like square root of t using the simple limit theorem. You have to normalize that random variables. But using lies, what you're saying is that Zn is behaving like mu. Order y is the same. That's all it's saying. But to show something like that, you need some power. You would expect this process. You should really, what it really saying that my process is going down every time it explodes because mu is greater than 1. So one would expect mu to the power n particles in level n. Saying that's it, right? Not too far away from that, with very high probability. So expectation is equal to, so mu n is nothing but the expected value. So how close are you to the expected value? What is it? Greater than by mu1 with very high probability is remaining bounded. Right now, I think one more theorem. Telling you something interesting, not a non-interesting matter. Really interesting. Okay, now we come to the most important, most interesting matter. Let's look at the process.
One in the previous slide.
Yes, question?
Even if mu is like not greater than 1,
Okay.
then also this thing
What will go wrong? Good exercise for you to check. And we can go wrong.
What's the question?
Then why do I care to claim that this is true for mu greater than 1? What do you have to put mu less than 1? What will go wrong? Think about, so don't take on math. Think about the physical process, the matching process. When mu is smaller than 1, what is the ratio of Z by mu you should think of?
There is no mu will go to 0, right?
Where is Z going, where is mu?
both are both
Then
will
it will go to 0.
Z will go to 0. Okay, and what will mu go to?
both go to 0, but very small.
Which is faster? Z is going to 0 faster than mu power.
Due to the power and essentially n tends to infinity.
Then it becomes exactly 0, right? At some point.
Okay. All sorts of peculiarities will start. Okay. So you should discover where the theorem, why the theorem. That will be interesting. You just understand what is something strange. Because when it's critical, there is going to hit 0 somewhere.
Yes.
So what does it even mean to take 0 by mu power? Is it not just going to 0? Identically going to 0. So you don't even have to worry about it. What we shown is that almost surely it's going to die. And if it's going to die, then it will achieve 0. And it's finite decision. Finite to 0. But yeah, okay, what happens? Okay, so now condition on survive. Survive means not existence. There are, in fact, unboundedly long things. Now, which is. These are very good arrows, so they are going off the link. By these letters. So the red nodes are the ones who are connected to the infinite tree below. While the blue ones have only a finite size. What do you want to find? You want to find the condition on survival. What is the distribution of number of red particles any generation? The question being, red points are connected to infinite trees below. Blue points are only a finite tree below. With the energy generation. So red points. Call it. The infinity. Mind is what is the distribution of red and white? Conditioned on survival. We did the opposite exercise. We conditioned on extinction, try to find how large is the population. Or what is the distribution of random variables? Here we are doing the opposite. Now what do you expect to us? Any observations? Make some observations and things are there. Easy to solve.
Red node has at least one red child.
At least one. Whatever. It is infinitely many.
And
Oh, one
in
level.
child.
Anything more you can say?
Blue nodes will not have any red.
Sure, we are not interested in blues. We're interested in the reds. But what you said, they did not say more than that. Said it has at least one child. But what is the property of that child? If I have a red node, I definitely have one more red node in n plus first generation. Right. Because otherwise it's not possible for me to be a red. Can you use that property to say something interesting? Going from level n to level n plus.
Number of red nodes in level n plus 1 should be greater than equals to number of.
Okay, that is a good problem. Yeah, it's not going to be helpful. Anything else?
Then you have two red nodes at n plus 1 given one red node.
Possible, yes. Because only the trees. So it could be that both of them are going to be. All I have told you there is survival. I am not saying that how many points are, right? What is the width of this survival tree? Could be many. Typically, that's what will happen. If it's surviving, it's like lots of things will go on. Let's start with the start, like the root form. What is the probability that the number of red nodes in generation 1 is k given as a in compute time?
First one should be red.
No, I'm saying, first one definitely there, because so that is with probability one. Talking about the generation of right below, so that's what my generation one always is, that's at 0, so that's trivial. The first generation, how many children do I have which are red, given that there is a survivor? We estimate it.
Z1 times expectation value of X will be the number of nodes in next generation, and times the
Very important.
Z1
They are estimating is the number of particles which are red.
which are red.
In generation one, that's why I did.
Should be number of nodes in the generation one and the survival probability 1 minus
Times.
so 1 minus theta.
Is that true? So these are raw areas. So definitely this one will not be true. You want to say something like that? This. Yeah, why is so I don't want to be good at this. Because I have only limited time today. Try to think this to what I want you to think about is I want you to think about what is probability of given a survey. Very important. Think about this. Okay, say and 1 minus theta you can call another thing. So that will keep your this. How should I calculate this now? Divided by this. What was this?
Survival given is the-
So did tell you any extra information? We are taking intersection of the one with the equal to the intersection. Solve it with the so given that I'm surviving, what? But survival given Z1 equal to K times Z1. Do I get any extra information? All the previous.
Z1 equal to that it is
Yes.
We are asking the reason. So it is like probability of surviving given Z1 infinity equal to K, will which always be equal to
So when you have Z1 infinity equal to K.
Yeah.
So the upper expression can be written as like probability of surviving given Z1 infinity equal to K. Yeah.
Open it another condition. What is the probability of survival given delta infinity equal to K? That is just one.
Yeah. Yes.
So I am getting only this. By definition, delta infinity means there is one particle, K particles who have infinitely many distances. So that automatically means you just limit one to that. Rather than writing delta infinity given survival, you write probability of survival given delta infinity. Okay. So now I know the denominator. How should I proceed further?
We should have K greater than 0.
K greater than 0, yes, that is correct. For K equal to 0, something is trivial. That probability is 0. That's not trivial. So this is all these computations. Okay. What more can I do? I can condition on Z1.
Yes.
That's the first thing I should do. With Z1 infinity a subset of that. Right? Z1 is the total number of red plus blue channel. Yes. I'm only interested in the red part. So I can always write this. So I'm going to write this as 1 minus. I have a condition that J had to be greater than K. What more should I do? Now, what can I simplify? So I have Z1 is equal to J, out of which some of them are Z1 in present.
Not 1 minus 2 times J.
No, I don't tell you just minus 1 there. All I have pulled out is probability of survival in the bottom.
Also, this the probability that we this one. Yes. Is it not J times 1 minus 5?
You look confused. Whatever. No, whatever you say, and you try to verify it is true. But think about whatever I said. All this put together is that one. The red guys are that one. Currently, I have Z1 is equal to K given Z1 infinity is equal to K given Z1 is equal to G. There is something that's very appealing. You wanted we anyway use this to claim this. So what was that appealing property which you used?
Binomial with J.
Something has happened independently. Total number of particles were there. K among them became special. And what was that special probability? Because going downwards, the survival probability is same. You start from the top or start from first generation. It still remains 1 minus 8. So what is very interesting?
1 minus eta to the power.
J choose K.
There are many possibilities in which you can do this. So
You need to do.
J choose K possibilities is getting there. Each of basically just process independent points on each of them with probability 1 minus 8. And how many possible ways you can generate K about that is then choose K. So I get
J choose.
you use this symbol or J choose K. This symbol.
PG.
Minus power K. Oops. What should we do? With 1 minus theta, you get a k. And theta, you get here. There is some extra probability.
PT.
This item, somehow, what do I know on this? There is P there, per generation.
Yes.
Okay, generation number 1, this is nothing but P generated. So, I will not simplify this. What will happen? We're going to leave it at this form, nothing more than this. Call it PJ. This is so. What was the computation we are making? Computing number of red points in generation 1 given something is survived. Why is it useful? I want to look at the whole process. Do you think it's a useful quantity to compute? Why did I go to the first generation?
For example, I want to visit this graph.
Yeah.
Then if I know if I know what nodes are will not end, like, then I can choose those nodes first to visit. And if I know from biological perspective,
I'm not asking this. What I really want to know is what is the distribution of data in infinity. But what I have told you currently is Z1 infinity. Why do you think that is sufficient? Why did I step on this?
Like for any node, what's the probability that there are k of its children are red?
Simple.
So instead of z1 infinity, you can write this x infinity.
Put this.
For any node, x infinity is the number of children, number of red children.
I told you earlier, I want to end generation to N plus 2 generation. Everything is symmetric wherever you put out. So I just go to the top and figure this out. That's what I really done. Now tell me how do I.
So you can ask the same question for Z to infinity,
Yes.
and then you can
It
find.
will be more messier. Because if I go 2 steps behind, things will be slightly messy. I want to somehow use the structure and go 1 step. For 1 step, I know what to do. See, if I start at any level, I can do 1 step above or 1 step below. This is what exactly I want to see.
Yeah, this is the probability that any node has k red children.
That's true. Why is that useful? How do I use that? Except that you don't need to do any more computation. All the computations are now done to characterize elements. So if you were to conjecture, whatever I computed essentially the distribution of red nodes in level 1 given survival. And that has come out to be a new distribution. This is P infinity K. Okay. If you wanted to conjecture the new distribution Z in infinity, what would you conjecture? That's what my conjecture would be. That Z is nothing but summation of these xi where xi are distributed according to P infinity. Whatever I showed you so far, that given that there is survival, this first level guys, Z1 infinity are distributed as P infinity. That much I showed. If you would like to conjecture, what you would say that this whole process, Z infinity process is nothing but summation of these x's, where each of them is distributed according to this. Just like how is the Zn process? There is nothing but summation of. This is what my Z is. Similarly, I can know, right, there is infinity with size infinities. That's what I would convey. With each of these xi infinities are nothing but distributed as pk. How do I go from this one step to another? We use induction. If you want. Is it clear what you are saying?
Yes.
So whatever branch line you gave, that's sufficient. 0 to Z1 is same as any red particle to its children n plus first element. That's all you need. Clear what you want. That is clear level. That my first level, how many children are red, is the same as at any level, my children, the number of children I have. There is no distinction. Everything is like. We're completely new branching process. Where the offspring distribution began. This is my original branching process. I'm conditioning on search outline. I'm looking at how many red nodes I will find. Saying these two are identically distributed. So now, what is Z0 infinity? And Z0. This is by definition. And this is one because by definition one because survival either of them. You can start now induction. So suppose that K2, N minus 1. Let's say distribution as. I can go to N minus 1 to N data. So how do I do this? N minus 1. Given that this is good, I need to go one more step. So this we know how to go from 0 to N. This is nothing but a branching process, we just decay. What do I need to show that from here I can go to the next step?
The red is
So Z hat K is the usual branching process. I don't have to worry too much. Because I just have defined it with a different distribution. So I know completely how to go from N minus 1 to N. There's nothing but that many more children with this distribution for each of them. Now for ZK infinity, what have I showed in the previous? But that is exactly the conditional distribution I will see for. What did I show for ZK infinity? What I showed last time was ZK infinity. That from the parent, the number of children which are part of ZK infinity have the distribution PK. That is exactly the same. So for going from here to the next step, this is the branching process of that distribution. Here from here to the next step also is a branching process. With exactly the same distribution as that.
That thing we need to prove, right?
That's what we proved in the last step. The punchline, which we said that going from 0 to level 1 is same as going from any this level. Because this is also red. Right? Red to how many reds we get. Similarly, red to how many reds. Looking at this is same as this, given that this K is going to infinity. See, a red point here is connected to, always connected to the top, as well as this could go on. So the same process being repeated from here to here or here. That is precisely the distribution you computed to the PK. And that I was just assigned to a new branching process. So I can go from this to one more step. And from this to one more step. So these implements are IID. IID net is also important. All the work was done as soon as we were able to compute one step problem. Then what is the probability that I have so many red nodes in level 1? Because that is going to be repeated over and over. And I will go. And what did I do? I smartly just picked whatever probability I got. I said this is my branching process. Because I know for this is exactly the same now. So it's cheating you want to call it. But in the process, what we ended up getting was this is a completely new branching process with a different distribution. So conditional survival, the process you should see with this. Now you can try to claim that this is always it has expectation greater than 1. You can actually explicitly compute it. There is a problem. Okay, let's start here. So, bit of news. I'm not here next week, so you won't have to take classes. But I want to each one of you to figure this out. So, conditionally, that's what your hunch was. It's not in expectation, it's actually almost sure. So you can also derive from here that in expectation as well. Yes. Otherwise, it's not. So I want all of you to look at this. If you don't want to prove it yourself, at least look up the book. It's also in the book. It is not nice. Now, if you don't prove, look at the many books. And just select one of you to come after that. One. So the next class will be February 27. And that's all for the day, which homework you do.